We are starting with the capacitors today. So in this, we're going to look at the formulas. We're going to try to solve an example as well, and then some solve examples from the Cambridge examinations. So according to syllabus, first we need to identify what is capacitance, and we need to understand spherical conductors and parallel plate capacitors. But we're going to talk about parallel plate capacitors first. We need to understand how the charging process takes place, and that will help us to understand how to solve numerical questions. So a capacitor is basically two plates almost placed in parallel in front of each other. Our batteries, mobile phone batteries, laptop batteries, even the batteries of the UPS are also a form of capacitors because they store electrical energy in the form of electric fields. Now, if you connect this capacitor to a battery, for example, let's say with a positive and a negative terminal, how the charging process takes place is important. So what happens is that the negative terminal of the battery starts producing electrons or starts injecting electrons on one of the faces of the plate. Now, what this causes is that the plate on the opposite side, which also has, let's say, a neutral charge at the very beginning of the process, if it is neutral, then it will most definitely have positive and negative charges before connection. Now, because of accumulation of those negative charges on one plate, the negative charges of this plate gets repelled and they go through the battery and start accumulating on the other side again. So eventually, all the electrons, or most of the electrons, or however much effort this battery can do, however much energy this battery can provide, those many number of electrons will be removed from one plate and will be injected onto the other plate. And at the end of the process, we will realize that the charge on both plates is same. If this is positively charged, then this will be equally negatively charged. If this has 10 electrons, then this plate will have 10 positive charges left behind because of those removed electrons from that plate, right? So this actually explains two things. One, that the charges on both plates will be the same, irrespective of the size of the capacitor. Two, the charging process slows down as it gets filled up. Why is it slowing down? Because if we look at the graph of the current through this circuit, the current is very high at the very beginning of the process when time is t0, and then the current starts reducing when the capacitor is fully charged. When the capacitor is fully charged, it will stop accepting any more current. Why has that happened? The reason for that is, and you can experience this in daily life as well, in your mobile phone charging. If you charge it from a very low percentage, it charges up very quickly. But the last percentage, for example, if it has to charge from 80 to 90% or 90 to 100, that will take a longer time in comparison to the initial charge. So why is that happening? So basically, since we are accumulating a charge or a negative charge on one plate, injecting more negative charges will become difficult as already there are negative charges present on that plate. So if you want to inject more negative charge, then you'll have to overcome the opposition of these negative charges that are already in those places. So that is why the speed of charging reduces with the passage of time, because it gets difficult with the passage of time if you want to inject more charges. Anyways, this is how a capacitor actually charges. Then we go towards this formula for Q equals to CV. What is the meaning of this formula? Basically, the formula starts from this idea of charge being proportional to voltage. Now we know from AS electricity and simple O levels that voltage is work done by the charge. So this is basically joules per coulomb. So the battery is actually the cause of this work done that it is doing on every charge so that it can move from one plate to another plate and eventually store that energy. So if I increase the voltage, if I produce or if I provide higher joules or more energy, or I do more work, it will cause for a higher movement of charge from one plate to another, and eventually the capacitor gets charged. Now, between all of this discussion and amongst this, we have to introduce a constant because of the equality. So that constant in this situation is, let's say, K. So this is Q equals to KV. Then we realize that this constant is actually a quantity called capacitance. Now, we are familiar with two of these quantities before from our previous knowledge. Q is charge, basically the number of electrons. V is voltage. Then what is C? C is capacitance. Now, what is capacitance? And it is measured in farads, right? What is capacitance? As the name suggests, it is basically the capacity of that capacitor to store charge. To put it into plain perspective, the energy stored by your mobile phone or the mobile phone's battery is much less in comparison to the energy stored by the laptop's battery. Similarly, energy stored by the UPS that is in your house. So this difference of capacity of storing energy is actually manifesting itself in this concept of capacitance. So let's say if I have a 10 farad capacitor, if I have, let's say, 10 microfarad capacitor, then this will be able to store less energy and this will be able to store large energy. And if you take an example from your house as well, we have water tanks in our houses, right, to store water. So a small tank would mean that its capacity is low. A large tank of water would mean its capacity is high. Similarly, for capacitors, capacitance simply means, in physical terms, how many electrons it can store for the current voltage and current charge, right? Okay. Then we move towards this idea of capacitance of a spherical conductor. That is a part of your syllabus. If you go above, we have to discuss spherical conductors. So a proof of spherical conductors is generally asked in P4. I've seen that question sometimes. So how to prove it? So we know that Q is equal to CV. And we know from electric fields, I will connect that video as in the description as well if you want to go back and check that out. So voltage is defined as Q divided by 4 pi epsilon naught R. Now if you separate this, this becomes Q divided by R multiplied by 1 over 4 pi epsilon naught. Now since that is a constant, that is why we are not dealing with it right now, because this is a constant. So we also know the equation that is V is equal to Q divided by C. We also know that V is equal to Q divided by R and 1 over 4 pi epsilon naught. So if you equate equation number 1 and equation number 2, because V is same for both of them, we land to the equation that is Q divided by C is equal to Q divided by R multiplied by 1 over 4 pi epsilon naught, right? We realize that this Q will get cancelled out, and if you cross multiply everything, you end up with an equation that looks like this. So capacitance is equal to 4 pi epsilon naught R. So what does that mean? It means that for a spherical conductor, let's say for a charge of sphere this size, its capacitance will depend upon its radius, or in turn you can say how big it is in size, because this is a constant, right? E is the permeability of free space, right? So if you increase the radius, you increase the diameter, you increase the size, the capacitance or the capacity of that sphere to hold charge, to store charge will increase, right? So this proof is generally found in the question sometimes. Okay. Now from the syllabus, we understand what is C, what is Q equals to CV, right? Now we're going to use this formula, Q equals to CV, to prove formulas for series and parallel, right? Let's see how that proof actually goes. So what does it mean that the capacitors are connected in series? That is, the concept exactly originates from the resistors combination, that capacitors are connected one after the other. And it does not matter that they are same, they can be different. So C1, C2, and C3. And they are going to be combined into a single capacitor of value CT as C total. So how do you do that for this situation? Now, before we start with this, before we move on with this, we understand that in a series combination, the voltage gets divided, right? So if I apply a voltage to this combination, let's say with a battery, then based on their capacitances or individual capacitances, the voltage will be divided, just like a series circuit, among these three. So I can say that if, let's say, this is the voltage of the battery, then voltage of battery is equal to V1, as in the voltage of capacitor 1, and consequently V2 and then V3, right? All right, so now we have the equation that is Q equals to CV, making V the subject of the formula. We land at Q divided by C. So the next step of this will be to replace all of these with this equation. So we are left with Q divided by C is equal to Q1 divided by C1 plus Q2 divided by C2 plus Q3 divided by C3. Now notice that in a series combination, the charges or the value of Q charges are same. Why are they same? Because when the battery is trying to do work for this system, what's actually happening is that from this terminal, the electrons are being removed and they are being added on this terminal. So if 10 electrons are added on this, then 10 electrons will leave that terminal and go to this one. and then 10 electrons will leave and go to this one because of repulsion, right? They're repelling each other, as I've just explained in the charging process, that their repulsion causes these electrons to move out or away from the plate, go through the battery, gain energy, and go back to the other plate. So similar thing is happening over here. So irrespective whether the capacitance is high or low, the number of electrons removed from each plate remain the same. So the charges on each plate are exactly the same. That is why in series configuration, we say charges remain same. So Q gets cancelled out as common from the whole situation because it's the same. So we are left with the equation that is 1 over Ct equals 1 over C1 plus 1 over C2 plus 1 over C3. So if you want to combine three capacitors in series and make them into one or simplify them into one, you'll have to use this formula. And of course, this is opposite to the resistors connected in series. So if we move towards parallel configuration, that would mean that capacitors are connected in this configuration. And again, I maintain the statement that it does not matter whether they are exactly the same or different. This could be C1, this could be C2, this could be C3. We want to convert them into a single capacitor of value Ct. This is where we actually conclude our proof, right? That these three can be represented as one. Similarly, these three can be represented as a single capacitor of value Ct. How to do that? So since we know that in this situation that we are having in parallel situation, what happens is that the charge actually coming from the battery, let's say if this is the battery, charge coming from the battery is going to be divided among three capacitors because the number of electrons can only be as much. If the battery can only provide 20 electrons, then there will be only 20 electrons. So it is possible that 8 of them go to this one, 2 of them go to this one, and 10 of them go to this one, right? So the charges are being distributed in this situation. Voltage is same because they are in parallel. Voltage is same, but charges divide. Because I know that the number of electrons are going to change or going to change their path or choose their path depending upon other circumstances. So I know that charges are going to divide. So total charge by the battery is equal to Q1 plus Q2 plus Q3. Then we go to the formula that is Q equals to Cv and replace it in this equation for the whole system. So this becomes total capacitance multiplied by total voltage, which is the battery voltage, equal to C1 V1 plus C2 V2 plus C3 V3. Now we've established that since this is a parallel combination, the voltage is exactly the same. So voltage gets common and gets cancelled out from the whole equation, and we are left with Ct equals to C1 plus C2 plus C3. So similarly, in this equation, parallel combination, if you want to combine them, you're simply going to add them together to convert it into a single capacitor, right? Okay, so we have done the proof as point number 4 and point number 1 and 2. These are complete. Now we're going to try to solve a simple question of capacitors to understand how to use these formulas in their true sense and meaning, right? So we have a question over here. In this, we have a 20 volts battery, and we understand that these are 6 microfarad, this is 10 microfarad, and this is 8 microfarad, this is 12 microfarad. So we understand that these capacitors are having values in microfarad. Now micro would mean power minus 6. Our first job, and what is required in the question? So they want to find out the voltage V1, V2, and V3 because we know that this is a parallel combination, so the voltage will remain the same. They want to know the Q1 and Q2, and we know since they are connected in series that charges will be the same. Then they want to know Q3 and Q4. We know that in parallel combination charges divide, so we also want to know that as well. So we want to find everything, right? So first we need to simplify the circuit. So we understand that these two capacitors are in series with each other. So we are going to use the formula for 1 over 6 plus 1 over 12 equals to 1 over 10. So capacitance, total capacitance in this scenario comes out as 3.75. You can verify this. This comes out as 3.75 microfarads. So the circuit actually looks something like this. So this capacitor is 3.75, and we encounter two in parallel, and we know that in parallel we can simply add them together. So this will become 8 plus 12, that becomes 20. So this is going to become 20 microfarad, Now again, we see that they are in series, and for series, we are going to apply the formula 1 over 3.75 plus 1 over 20 equals to 1 over C. I am not involving the microfarad symbol right now because it does not serve any purpose. I understand that micro is going to be a part of the answer as well. So when you fully simplify this, you realize that you are ending up with a 20 volts battery and a single capacitor of value 3.16. So this is 3.16 microfarad, which means that this whole circuit can be simply replaced by a single capacitor of value 3.16. But of course, you are not going to find this from the market. This is just for solving the question. Okay, now first we find the total charge injected in the circuit. So how do we do that? To find the total charge, we apply this formula for the whole circuit. So capacitance will be taken not for 6, not for 10, not for 8, not for 12, but the full capacitance, the equivalent capacitance of the whole circuit. So that will be 3.16 into 10 raised to the power minus 6. What is the voltage that you provide to the circuit? We provided 20 volts, so this is going to be this way. So the answer that we get in this situation is 63.2 microcoulombs. So this is the total charge that the battery has dispensed into the circuit. Now charge is the number of electrons. So we can say one way or the other that the battery has released 63 electrons into the circuit. I'm ignoring the microfarad or the microfactor right now for the sake of discussion, but the battery has released 63 electrons in the circuit. So now visualize that if 63 electrons come to this plate, 63 electrons will be repelled to the other plate, and it will again repel 63 electrons to the next one. So we understand that in series combination, the charges remain same even if their capacitances are different. It does not matter. Why? Because they cannot control it. If one capacitor receives 63 electrons, it has no choice other than to repel those 63 electrons to the next charge, to the next capacitor. So similarly, this is the idea that we're going to use to find out the respective voltages of these capacitors, because we know that the charges on both of them are same. So we apply Q equals to CV on both of them independently because we know that charges are same. So we know a few values. So in place of charge, we will replace 63.2 micro equals to capacitance of that individual capacitor, which is 6. I know that. So 6 into 10 raised to the power minus 6 multiplied by V. Similarly over here, 63.2 into 10 raised to the power minus 6 equals to that other one is 10 micro. So that will be 10 minus 6 into V. And when we solve this, we find that this voltage comes out as 10.5 volts and this voltage comes out as 7.9 volts, right? So now we can go back to the situation and we can say that approximately 10.5 volts being used by this one and 7.9 being used by this one. Now we can simply calculate the voltage for the third party as well, because I know that the total voltage is 20 and I know that 10.5 and 7.9 are being used by these two combinations. And the rest of the voltage will be available for that parallel combination. So I'm going to solve the parallel combination independently. It looks like that as if 10.5 and 7.9 voltage were taken away, right? And what we are left with, what voltage we are left with is basically 3.16 volts. So 3.16 volts are available for the rest of the combination of the parallel combination that is left out right now. So for this one, now we understand that the charge injected by the battery is basically 63.2 microcoulombs, and the voltage at which it was injected is 3.16. I again repeat that 63 are again repelled to the next circuit. That is the same charge that was generated in the whole system that was provided by the battery. So one of them is 8 microfarad and one of them is 12 microfarad. Now we want to find out, we know that the voltage is going to be the same on both of them because they are connected in parallel. But we want to know how much charge goes to this one and how much charge goes to this one, because I know that in parallel combination, the charges or the number of electrons divide because they have two choices, right? So for both of them, we're going to solve it individually. So we apply Q equals to CV once again, Q equals to CV once again. So we don't know what the charge is going to be, but we know that their individual capacitance is 8 microfarad. The voltage that they have is 3.16. Similarly over here, Q is equal to its capacitance is 12 microfarad, so 12 minus 6 into 3.16, the voltage that was left behind. So we find that the Q of 8 microfarad comes out as 25.3 microcoulombs, and this charge comes out as 37, I think, yes. So 37.9 microcoulombs. Now, if you add them together, you will again get Q total as 63.2 microcoulombs. So we have this guarantee that this 63 was divided into two branches based on their capacity. So you can see that at same voltage, since 12 microfarad was a larger capacitor, it was a larger tank, it held on to larger charge. It can store more number of electrons for the same amount of applied voltage, right? So you can go back and backtrack your, this is a question I've arbitrarily constructed. You will not find this question in the past papers, but it helps us to understand how to solve a capacitor system, because we are going to encounter these questions one way or the other in the next phase of the video. Now we come to this question we have from May, June 2016. Now you can find the answers of question number 7 part A in your marking scheme. I would advise you to not go into the detail of this one. What you can do is just memorize the answers and just get on with it. I would not advise you to memorize, I would not advise you to search them, because the problem is that the devices that they've mentioned in this situation are actually not a part of your course. A few of them were, but not all of them are now. So I will just advise you to just memorize the answers and be done with it. So the first one is storing energy. Most definitely storing energy, as we have in our mobile phone batteries. They are supercapacitors, or a fancy name for that. We have oscillator circuits. Oscillator circuits basically were actually tuning circuits. And then we have tuning circuits. Your FM and AM radio actually uses tuning circuits. And then we have timing circuits. You may have noticed that there are few electrical functions that happen periodically. For example, if you give the indicator of your car, it blinks periodically. Who is telling that indicator to blink periodically? A capacitor system, right? So how it actually works, what the system looks like, is beyond the scope of your syllabus. Anyway, so I will just advise you to memorize them. So moving on to the question, the capacitances are unknown. You can find this question in past papers as well. These two are identical in parallel, so they will share equal charge, right? So it tells me that the potential difference between terminal A and B is 12, which means that there is a 12-volt battery connected between these two terminals. The battery is 12 volts. And he tells me that there are 3 microfarad capacitors. It tells me to find the value of C. Now, it also tells us that the total capacitance of the system is 4 microfarad. So if I had to convert this into a single capacitor, that would have a value of 4 microfarads. So I'm going to apply the equation that we've learned in the lesson from series and parallel combination, from this combination, right? What happens to series, what happens to parallel, in one go. So since they are in series, what I'm going to do, I'm going to apply the formula 1 over C plus 1 over C. And I know that they are in parallel. In parallel, they get added together. And when they do get added together, they are going to convert into a single capacitor that is again going to come back as a series configuration. So I'll have to write down 1 over 6, 3 plus 3, simplified as a single capacitor, replaced in both of their places. This will be cancelled, this will be cancelled, and a 6 microfarad will be replaced here. So then it will be in series. So then again, I will have to use 1 over C for it to be solved, right? Okay, so this should be equal to 1 over 4, because this is given in the question that everything in this system equates to 4. The total capacitance equates to 4. Now, from this point onwards, it's your job to perform algebra, but I will advise you something. You can bring this 1 over 6 on the other side and then simplify this 1 over C plus 1 over C. And you'll find that C is equal to 4 microfarads, right? So this comes out as 4.0 microfarads. Then he tells me calculate the magnitude of total positive charge transferred. So to do this, we are going to use the formula Q equals to CV. I know that the whole system actually simplifies to 4 microfarad, and I know that the whole system has access to 12 volts of voltage. So to find out how much charge, how many electrons it can store, I can simply write down 4 microfarad multiplied by 12 volts. So my answer comes out as 48 microcoulombs, which means that it has stored 48 electrons, for the sake of discussion, 48 electrons in the whole system. Now be advised, the battery transferred 48 electrons, on this capacitor. It repelled 40 electrons, 48, and gave it to this one. It again carried 48 electrons in this combination. Now, since these two capacitors are identical, they are going to divide these charges amongst each other. So 24, half of it will be stored on one capacitor and half of it will be stored on one capacitor. If you want to understand what happens when they are different, you'll have to go through this question again or see this video again, that if the capacitors are different, how the charges divide amongst them even if the voltage is same, right? So go back and see this one again. Now, he asks me, what is the capacitance, what is the charge on capacitor C? Now, we've established that in series, no matter even if they're identical or different, the charges, the number of electrons remains the same. So it will exactly be 48 microcoulombs as we got in the previous answer. But when he asks me about the 3 microfarad capacitor system, these ones, I realized that since they are in parallel, the charges, the number of electrons will be shared. The current is divided, so the charges will be shared. So half and half. So I get only 24 microfarad on this one, right? Okay, now we get to this question. This question is taken from February, March 2016. And this is actually the B part of that question. Now, let me show you an animation that actually shows what's actually happening. Students generally get confused what's happening in this situation. So what he's doing is that first the switch is in position A. So the whole current passes through the circuit and the capacitor gets charged. Then he moves this switch to position B and waits for you to find out what the answer is going to be, right? So no need to worry. I'm going to show you an animation that actually performs exactly this function. So then you can visualize how this question is actually behaving or performing, right? But let me pause this for a second. As you can see, this is an animation from PHET, Colorado. This animation is taken from them. So what's happening is that this capacitor currently has a positive charge on one plate and a negative charge on the other. And notice that on the other hand side, we have another circuit that has a load connected to it, that has a bulb connected to it, right? So the capacitor right now is fully charged, okay? Now, if I move the switch position to this position, nothing happens. The capacitor stays charged. But if I move this to this position, notice what happens as I release the mouse click. So the capacitor's energy is now going to go back to the bulb and the capacitor fully discharges. You can notice that all the charges have disappeared from the capacitor. This is exactly what happens with your mobile phone's battery. You charge it with your charger and then you use it throughout the day, right? So you come back home, you charge it again, and then you use it again, right? Now let's look at the voltage by connecting the voltmeter in parallel at these two locations, right? And see how the capacitor discharging behaves. So right now there is no voltage, but if I take the switch from, let's say, this position to this position, the capacitor gets charged. Let's move the probe at this location so that we don't have to check the charge again. So now the capacitor has a voltage of 0.35. Okay, I can increase the voltage of the battery and you can see that the voltage of the capacitor right now is 0.5. When I move the capacitor to the neutral position, okay, the capacitor holds its energy. It holds its charge because it's not being utilized. When you move that towards this, now notice what happens with the voltage. The voltage starts decreasing because it is dumping its energy from its own electric field into the external bulb or load that is connected. That is how the battery gets discharged of your phone throughout the day, right? So I hope that this change over switch position or this changing over action that is represented in that question is clear to us now, okay? So coming back to the question, I hope that we understand how this switching position is actually working, right? So let's move on towards solving the question. Okay, so it tells me that the switch position is switch position A right now. So it's actually part of this circuit. In a simplified format, that would look something like this: two capacitors in series. Okay, it tells me to find out that combined capacitances, they are in series with each other under the circumstances. So I will use 1 over 200 micro plus 1 over 600 micro equals to 1 over CT. So simple algebra leads to the final answer of 150 microfarads. What does that mean? It means that in place of these two, I could have connected just one capacitor of 150 microfarad capacitance. Then we move on to the question, the charge on 600. Now this is a trick question. You see, we know that since both of them are in series, whatever number of electrons the first one gets, the second one gets the same number of electrons. Now, when I say number of electrons, the charge is going to be equal on both of them, irrespective of their individual capacities. This is what we just discussed in the proof of series capacitors. So either it was 600 or either it was 200, it wouldn't matter, because I will simply find the charge on the whole system, because I know that whatever charge is in the whole system is what the battery actually provided. So the battery provided these many number of charges to this charges, power minus 6, into the voltage that is connected or available is 12 volts. So your answer comes out as 1.8 power minus 3 coulombs. So 1.8 into 10 raised to power minus 3. So the battery has given 1.8 electrons to the whole system. Okay. Then tells me to find out the potential difference on the 600 microfarad, which is again easy. I understand that a series combination voltage gets divided and the charges remain the same, right? Okay, so I know, for example, I will be using Q equals to CV, but for in place of C, I will use 600 microfarad. I know that because I'm finding for this one, voltage is what I need to find out because that is asked from me, but I don't know what to put the charge here. Now, again, the charge will be 1.8. Why is it 1.8? Because the number of electrons passed on from the battery in a series combination remain the same. So this is going to be 1.8 power minus 3. You simplify this, so the voltage you get after this is going to be 3.0 volts. So this is 3.0 volts, and most definitely, if the 601 gets 3.0 volts, this one will get the remaining voltage, which is 9 volts. Although the question is not asked, but for the sake of discussion, I'm pointing this out right now. Now, in the next part, it tells me that it is changed from position A to position B. The changeover has happened from this position to this position. Okay. All right. So now it tells me that what will happen if it has discharged 50% of its initial energy. Now, one topic that I would like to remind at this point is that the energy of a capacitor can be found by the formula half CV square, right? Or the formula that is given in the syllabus as half CV square and half QV. The formula can also be used as half QV. Okay. Now, one more thing or one more point at this location or at this point is that sometimes he asks you why there is a factor of half. So what happens is that if we do draw a graph of charge and voltage as this one, the battery does this much amount of work at a certain amount of charge and at a certain amount of voltage. The battery has done this much amount of work. But when you demand that same energy back from the capacitor to give it back to you, the capacitor is only able to give you half of the total energy that you have provided from the battery. So if the battery has spent 10 joules, the capacitor can only give you back 5 joules. It asks you, or the examiner asks you, where has that rest of the 50% energy gone? And that is why there is a factor of 1/2. Where is that energy? So that energy is lost as heat in connecting wires. So the very wires that are responsible for carrying the charge throughout the circuit are actually the cause of loss of energy. Okay, so he's asking me to find the voltage at 50% energy. So first we find out the actual energy, the initial energy. So that would be half CV square. So 1/2, the capacitance is 600 microfarad, power minus 6. Voltage of that is 3 square. The answer comes out as 2.7 millijoules. So this is 2.7 into raised to power minus 3 joules. Now, since I want to find the 50% voltage, so I'm going to divide this number with 2, and the half energy comes out as 1.35 into 10 raised to power minus 3 joules. So I use this equation to find out the voltage again. At this energy, how much voltage will it sustain? So 1.35 into 10 raised to power minus 3 equals to half. Capacitance is 600 into 10 raised to power minus 6. And this is V square. One thing students ignore at the end of the equation is that a square is there. If you take this multiplication over there, you take this into division, then you'll have to take the under root at the end. So the voltage comes out as 2.12, which can only be written down as 2.1 up to 2 significant figures. So if this capacitor was discharging through the circuit, then it would have had its 50% energy dissipated, 50% energy taken at merely 2.1 volts, right? Okay, so I hope you understand how to use these equations as well. All right, now we move towards discharging of the capacitor. This topic requires just a bit of more understanding, and for that we'll have to use a calculator. First, we need to understand how the discharging actually happens. So to go towards that, we're going to observe this graph. So this is how discharging takes place. At the very beginning, it has the voltage equal to the battery voltage, and then it starts losing its energy through the circuit or through the load, right? But okay, so how does that happen, and what is the value of this time constant, and what is a time constant? A time constant represented as tau equals to RC. What is RC? So basically, he tells you that whatever capacitor, whatever battery was used to, let's say, charge a capacitor, when that same capacitor is used in a circuit with a certain load, with a certain resistance, as a battery, for example, if your mobile phone, then you use that battery for the rest of the day, then your mobile phone circuit is the resistance. So how long or after how much time is that capacitor going to get drained? Is it going to get finished? The same concept applies. How much time will it take for it to get charged? So it depends on the resistance of the circuit and depends on the capacity of that capacitor. If the resistance is high, most definitely it will take a longer time. If the capacity or the capacitance of the capacitor is large, for example, a small battery of the phone gets charged quickly. Large batteries of the phones get charged later, right? Similarly to the water tank example, if you have a tank in your house, which is very large in size, it will take longer time to get charged. So this time constant actually tells you how much time this capacitor system is going to take to get charged or to get discharged. Now, what is the importance of this value? This is not generally discussed in the classrooms, but I'm going to discuss it anyway. What is the meaning of time constant? What does it tell me? What is it trying to tell me? So time constant actually gives you the idea how voltage, charge, and current are going to behave during the charging and during the discharging process. So one time constant tells us that there is going to be a 63% increase or decrease in comparison to the previous value. For example, if the time constant for a capacitor is 5 milliseconds, so it will go from 0 volt up to 63% of its battery voltage within a time of 5 milliseconds if it was connected for charging. And similarly, the 2 time constant will mean that it will go up to 84% of its original value, which is again a 63% of this one. So let's ignore the complex mathematics. Let's go to the final answer. So for any capacitor system at exactly 5 time constants, it will attain its 99.9% of its peak value. This 5 time constant is an important factor because this is what helps us to identify how long is it going to take for any capacitor or any battery to get charged. That is how mobile phone manufacturers or even your laptop predicts how long it will take for it to get charged, because it knows its time constant and it knows how much energy is being fed into the system. We're going to do the same thing, but before we do that, we need to understand this equation, which is referred as point number 3. It tells you that we need to understand this exponential equation, which is x is equal to x naught e raised to power minus t divided by RC. Now we know that this RC is basically tau. This is pronounced as TAU, tau, right? So in this equation, t will be of your choice. You will put t of your choice and it will give you the value of that respective situation. So what is going to be represented in x? So x will be voltage. So this is a voltage equation. It could be for charge, right? Q, that is charge. And according to the syllabus, we have it could be the current as well, right? Okay. Yes, it could be the current as well. So this equation will be modified. If you're representing voltage, then this equation becomes V equals to V naught e raised to power minus t by RC. Representing charge, it will be Q naught t by RC. And if current, then it will be I is equal to I naught e raised to power minus t by RC. Now notice that this equation is for discharging purpose. So if, for example, we go to this situation, this is the graph where this equation will be used. So this will be a representation of x equals to x naught e raised to power divided by RC. And over here, this is a charging equation, although this is not a part of your course, but for the sake of understanding, this system is defined as x equals to x naught 1 minus e raised to power t over RC, right? Now let's get these values. Let's try to see whether we get these values after the first time constant, the second time constant, the third one, the fourth one, and the fifth one. For the sake of example, we're going to take the time constants to be 5 seconds or 5 milliseconds. So this is going to be 10, 15, 20, and 25. We're going to use a calculator for this function and see whether we get these percentages or not. Is this exactly going to be correct for the discharging purpose? It is going to go this way when it is discharging. So that will employ this equation, which is this one. So for the first time constant, that is 5, for the sake of example, the discharging and the charging give you the same answer. But as you move away, the discharging starts reducing its value and the charging starts increasing its value. So let's look at this from the charging perspective, and then we're going to go towards the discharging perspective. So here we have the equation for the discharging and charging. Notice that for the very first value, if I calculate, and notice that I've chosen the time constant, that is RC, to be 5. It's my choice. It's going to be given generally in the question that the value of R is this, the value of C is this, so the time constant can be chosen from that. Now if I press calc and I choose 5 as my first answer, I get 63%. So at the very first time constant, we get up to 63% of the original value, which was 0. 0 up to 63. Then 63% of that will be 86. So to press calc again, we go to 10, the second time constant, we get 0.864, which is 86.4%. So this is tau, this is 2 tau, this is 3 tau, this is 4 tau, and this is 5 tau. So you will notice up to the 25th or the 5th time constant, if I calculate this as 25, we get 99.33%, which is almost equivalent to 100% of the voltage, right? So this is how we visualize that. And if you try to draw the discharging graph, then you simply delete this and try to calculate this again. So that by that method, we're going to get this graph. So after the very first discharge, it will go to 36%. It goes to 36%, or you can say it has dropped from its original position up to 63%. So it drops 63%, goes to 36. If you calc, this is the tau, this is going to be 2 tau or second time constant at 10 seconds, you get 13%. So this will be the current voltage, that is almost 13.5%, which of course from the very beginning will be a fall of approximately 86%, which was actually this one for charging, right? So time constant's importance is in terms of the time taken for the charging, and up to 5 time constants. In engineering standard, it is taken as maximum or full charge. Anything more than that actually gives you the same decimal place again and again. So if I put in, let's say 25, and then I put in 30, for this case, let's say I put in 30, which is more than 5 time constants, I get 0.0024. Now, no matter how many times I put in the values of the next time, this value will not become 0. And even if it does, it's going to become 0 after a very, very long time. So at 5 time constant, universally accepted that it will be the maximum value that this system can achieve, right? So let's try to solve this question. This is taken from October, November 2022, paper 4.2. We're going to try to solve this. So the first question, he asks you about the shape of 6.3. Notice he's asking about 6.3. What's happening in 6.3? So at the very beginning, in the discharging process, the voltage of the capacitor will be equal to the resistor. So the very first point is that the voltage of capacitor is equal to the voltage of resistor. We just have to lay down the observations. And the current is decreasing, right? and it is decreasing because we are losing charge, and we are losing charge because the voltage is decreasing, as we can see it from the graph. Okay, and we can also see that the rate of decrease is also decreasing. Now, what does this mean in the marking scheme? It is just one way to say that the gradient at the very beginning is high and at the very end it is low. So even when it is losing its energy, it is going to lose its energy very rapidly at the beginning, and then it is going to lose energy very gradually throughout the system. Okay, all right. So let's try to solve the question. It tells me to use the figure 6.2 and the figure 6.1 to find out that the time constant is actually 5.5 seconds. So I'm going to go back to 6.2, figure 6.2. We can see that the very beginning value, or at the very start, it is going to be 0.90. You can see that from counting the boxes. So our Q naught, or the very initial charge on the capacitor, is 0.90 millicoulombs. And since we want to find out the time constant, the value of tau should be equal to 5.5 as given in the system, right? But we don't know that yet. So the value of t that we're trying to find out the time constant at should also be tau. It's something like this, that the power of e raised to power t over rc, the time that we're putting in is actually equal to rc. So if you replace rc with rc, you get 1. So it doesn't matter whether it was 5, 10, 15, or whatever the time constant was going to be. What we're trying to find out is that the time constant is 5.5. What you could have done is taken two coordinates. For example, you could have taken these two situations, or you could have taken these two situations and then compared them to find the value of tau, or the time constant. But that is going to take a lot of time. So what we're going to do is we're going to assume that since we are taking the time for the first time constant, we can assume that the value is going to come down by 36 or up to 36%. So let's put in the value of Q is equal to Q naught e raised to power minus T by RC. Now we know that Q naught is 0.90 millicoulombs, and the value of this factor, which is e raised to power minus T by RC, since this negative T by RC has been equated to 1. Why did we equate it to 1? Because this is what we're trying to find out. We want to find out after the first time constant. So the numerator that we put as our choice and the denominator are exactly the same, right? So this is going to come out as 1. So this becomes 0.36. And you can see this from the falling discharging graph over here. There is a 36% current voltage and 63% drop. So the current voltage that we are going to have, or the current charge that we're going to hold, is only 36% of its original value. So the current charge comes out as 0.33 millicoulombs. Then you go back to the graph and you find out from this graph that 0.33, this is 0.09, so 0.33 is somewhere along this line, counting the boxes, and you go back and you find 5.5 from the graph. So from this point onwards, you have to go to the graph to recheck that the value of time t comes out as 5.5 seconds. Now the questions that are given to you in the examination for as show that the time constant is 5.5, these questions exist generally so that even if you're unable to solve the question, you can take this value to the next part. So this is what happens in the next question. He tells you that use figure 6.2 and 6.3 to determine the capacitance in microfarad. So we're going to use the equation Q equals to CV, and we know that we want to find the capacitance. So capacitance becomes the subject, Q divided by V. Now, since we want to find the capacitance, we will take the maximum value. So we know from the previous part, Q naught was 0.90 millicoulombs, and V naught has to be taken from the second graph, which is this one. So the peak voltage value that is over here is 7.5. You can open up the question and count the boxes. 7.5 volts. So replacing all these values in this equation gives me C is equal to 0.90 multiplied by minus 3 divided by 7.5. So capacitance comes out as 120 microfarads. So this will be 120. Then he asks you about the resistance. So we know that the tau is equal to RC, and we can simply replace the first time constant and then find R as capacitance is 120 into 10 to the power minus 6 microfarad, but the resistance comes out as 45,800 ohms, which can be simplified as 46 kilo ohms or 46,000 ohms in this question.